and this is EdTech Remix. Today we're going to be talking about computational thinkers, computational thinking as one of the 7 ISTE student standards. And with me today we have, we were able to find just a beautiful, for those of you that are only listening and not viewing here, we have a beautiful 1982 circa Apple IIe computer with the 5-inch floppy drive here.
A true floppy.
True floppy. And we actually have the Webster's New World Spelling Checker 2-disc set right there. So if I wanted to check my spelling based on the words that were around back then, pop that baby up, slide that in there, and if it was plugged in, the light would come on, and about 40 minutes later we would have the
good spell check.
The very simple text-based program that was the spell checker, the Webster's spell checker back then. But the reason I have this out in front of me is because when I was at Shumway Junior High School in 1982, yes, I'm that old, this was, everybody, the only way you used basically a computer was you programmed. Mm-hmm. I mean, it was basic technology. Oh, wait a minute, you've got some guides there, don't you?
We do. We have the guides.
Some of the long dead programming languages like BASIC and COBOL and a few others, and those are actually, those I think are from a VT220 deck station, which for those of you that have been walking this earth as long as I have, that was like mainframe computing for programmers, and that was what it was all about. I mean, computers back then, we didn't have the internets, we didn't have graphic user interfaces. It was all about text lines and commands and all that kind of stuff, and that's what we're going to talk about today is, well, not really, but we're going to.
It's funny, one of our other guests that we just had on a little while ago had mentioned stealing or borrowing the Apple II down and from the librarian and taking it down to his classroom.
Yep. Yeah.
Here it is.
That was portable technology in 1982. Yes. Oh, yeah. All right, so computational thinking, this is one that we're going to have to kind of explain because I think there's going to be some confusion for those of you listening at home around, how is this different from computer science? How is this different than coding?
Yeah.
But the definition that ISTE's come up with for this standard is that students will develop and employ strategies for understanding and solving problems in ways that leverage the power of technological methods to develop and test solutions. So it doesn't say anything about coding there.
It doesn't, no. And I think in our district, Mark is probably being humble here, but he's led the way on kind of shifting the mindset of our district away from coding. And not that there's anything wrong with coding. Coding is a very, very valuable skill. But it's maybe narrow. Maybe that would be my only thought on there. And Mark's done a lot of work on kind of opening up our discussion around kind of switching the conversation from coding to computational thinking, where it can be used as a way to creatively solve problems across all discipline areas.
Yeah, I mean, it's really intriguing because I'm a humanities major, so just point of reference, in 1982 when the geeks were at the computer lab at the Apple lab, the Apple coders, who now are all probably, CEOs of, Silicon Valley companies, and here I am doing a video podcast from Vancouver Public Schools. Not that I'm not excited to be doing that, but anyway, they probably did a little bit better than I did from a programming standpoint. I just that wasn't my bag. Yeah. I've never been a computer programmer, but I'm really, really intrigued by this one. This is of all the standards, this is the one I'm most excited about talking about with.
Yeah, and I think it's really accessible for all levels too. Yep. So when you go to coding and just focus on that as the conversation and the skill, and again, there's nothing wrong with that. It's a great skill to have. And it can even be scaffold to where you're doing block coding before you're actually writing a language. But I think one step above that is you can have these type of skills and activities connected to computational thinking that is far beyond and removed from coding altogether at a very, very young age and our more wise users as well.
This last weekend I was up at the bilingual conference, the Washington Bilingual Conference, and presenting with a couple of colleagues that are ELL teachers, and we did an activity that we didn't use computers, they didn't use devices at all. We actually built algorithms using Lego pieces.
Yeah, absolutely.
And, so it can be very, very simple. So let's try to make it simple. We'll pull out a guest here, a really fantastic colleague who will explore computational thinking with us. We'll be back in just a moment.
All right. All right, well, we have Wayne Johnston here joining us today. He's one of our instructional technology facilitators here in Vancouver Public Schools. So, Wayne, would you tell us a little bit about yourself, your experience, and maybe how you got connected with this?
And why are you talking to us about computational thinking?
Yeah.
Sure. All right. Well, thanks for having me on today. I was an elementary school teacher for 10 years before being an instructional technology facilitator. And this is my third year doing that. And I've gotten into working with students and teachers around computational thinking as a great framework for solving problems that fits in across curriculum areas, across subject matter.
Yeah. And you've been doing some presenting too, right? I think you presented at the Northwest Council for Computer Education on hummingbirds, and so you've been taking your learning on the street too.
I have, yes. So did a workshop at that conference up in Seattle with Bird Brain Technologies and using some robotics equipment in the classroom. Oftentimes, the idea of computational thinking as a problem-solving framework comes into mind for students with that as they're trying to use that equipment to build something that they've made and figuring out how to get the right movement, how to get the lights to work, how to incorporate sensors.
Sure.
So that comes into play there as well.
So as an ITF in Vancouver, you've got all these toys, all these initiatives, you've got all kinds of stuff going on in Vancouver, which is really great. And you, I know, just because we've done some work together, you've kind of gravitated to this idea of robotics and computational thinking. Can you kind of talk about why you've gotten so excited about that?
Yeah. Had some experience in doing coding with kids initially. And then the robotics came in as a way to kind of bring that code to life. Coding can kind of live on the screen and not really have a tangible aspect to it. And then when the kids have the robotics equipment, they can tie that into a content area they're working with, and then use their coding skills to bring their creation alive. And that ties into work within maker spaces that I've been involved with too.
And you've been doing some work with Digital Promise as well, right? You've been part of some of their advocacy around both making and computational thinking.
Yes.
Yeah.
Been in a cohort with a handful of school districts across the country about maker learning and working together and collaborating with other educators around the nation. And they have a wealth of resources around computational thinking that are great for educators.
Yeah.
I think one of the things too that comes to mind in talking with Wayne, I had the privilege to work with him on a ISTE family code night at Hauk a few months back, and it is very much code centric. But Wayne took a step further, and prior to getting into the coding portion of that with the families, he actually went through a whole slide deck on computational thinking, and I've been part of that. I've been part of that event multiple times, and most often we just cover the code part. But I think adding that layer to it really was able to connect not only the students, but it connected the families and those parents that were there with them through a broader framework. I mean, you called it a kind of a framework for solving problems. I think that's a good way to look at it.
That was a great experience, and giving parents the kind of larger umbrella, as I've heard you speak to, about computational thinking being the bigger picture, so to speak, and coding being one element of that can be valuable on its own. Did the Lego algorithms activity with the families there, and as a way to sort data, and the families seemed engaged and seemed to enjoy what they learned.
Well, I remember when I was there that night too, one of the stories I heard, one of the tables in the back that I was standing next to talking about, and the kids did a really good job at that. They were sorting colors of Legos based off of the prompt you gave them. But one of the parents turned around and said, if they can sort these so well, why can't they sort their laundry at home?
That's a practical application
Right.
of computational thinking.
Yes. Yes.
All right, let's take a look at the indicators.
Okay, so just like the rest of the ISTE standards, there are 4 indicators connected to this standard. So we'll kind of go through each one, and whatever initial thoughts you might have on it, you'll share with us, and we can kind of have a little discussion after each one. So the first one, 5A, students formulate problem definitions suited for technology-assisted methods, such as data analysis, abstract models, algorithmic thinking, exploring and finding solutions. So initial thoughts on that. How have you seen students interact with kind of some of those concepts? Or
those are some phrases that regular classroom teachers don't see very often.
No.
Yeah. I mean, data analysis, abstract models, and algorithmic thinking. That's new language for many teachers. So how are you kind of bringing that into the classroom so that it's not like overwhelming for the teachers and the students?
Yeah. Typically, some time to plan and work with teachers beforehand, so that they can ask those questions in a safe space when I'm there with them, and we can discuss some of that, and they get a little bit more comfortable with it, as well as kind of seeing the big picture of what this lesson is going to look like, so they kind of understand where we're going. As for a lot of teachers, as you said, this is new territory. I think in this standard, what really rings to me is the idea of students defining the problem.
Sure, it's excellent. Yeah.
Just those first few words, that can be difficult for students to do, and I think they need practice with that.
Yeah.
And so defining the problem, narrowing it down, what the problem actually is a great skill, and that takes practice and repetition for them.
Yeah, and I think one of the other things, and I mean, Mark's absolutely hit it right on the head too. Some of these terms are difficult to put into your regular classroom, whatever that might be. And I think making connections to what a teacher and student is already doing to those terms, So one of the examples I know that was given to me, this is not original, but when you're looking at like proofreading, right, that could be looked at as debugging or maybe data analysis, or and making those connections with teachers, I think, can be really, really helpful. That these aren't big, new, scary ideas. That it's probably a lot of things you've already been doing, but maybe putting a different lens on when you start to talk about it with your students.
The idea of process. I know that when we did the first workshop on this last August, we had some, I think they were either kindergarten or first grade teachers in the mix. And one of the things he said, well, this is like teaching the kids how to line up and go to recess or go to lunch. And it's like I had never really thought of it that way, but that's essentially an algorithm, and the variables is that little Jimmy on the way to the recess throws up, or there's guests in the audience or they're in the hallway as they're going down there, and people get distracted and whatever. But this idea of algorithms kind of just being part of our daily existence without realizing it, that's really part of everyday existence in the classrooms. And
I think to Wayne's point too, the importance that students can define a problem is and be clear on that. I think is key. We do that. I remember having a stats class in college, and the amount of process went through when we have a problem that we're looking at that we're trying to collect data on, but really through all these cycles of, is that really the problem? We may come up with a completely different problem. So knowing what questions to ask during that process, and I would agree with you that I don't think our students have enough practice or get enough practice on having the ability to ask those questions and define that problem from their viewpoint or from their context.
So the next standard is students collect data and identify relevant data sets, use digital tools to analyze them, and then represent data in various ways to facilitate problem solving and decision making. I've learned a little bit over the last 9 months, and that sounds to me to be basically algorithmic thinking. That's kind of some of the building blocks of computational thinking. So what are some ways that you kind of, what have you done with that in your work with students and teachers?
Deciding which data to collect, and then how to organize that so it's meaningful is a big step for the students I work with, primarily elementary school students for most of my experience. So sorting that data out, what am I going to collect? How am I going to organize that so it means something tied to the problem I'm tackling and ultimately a solution I'm trying to work towards. Is a big piece of that one.
Are there some examples of data that you've used in those activities with students? Or what are some places where you can kind of pull the data, like social studies, science?
Science is an easy one, like plant growth. Most of the elementary rooms, do kind of a unit on plants. And so the plant's growing, obviously getting bigger, but what data are we going to collect? If we're measuring its height, and then what variables are we going to factor in if it gets watered every day or twice a week or those kinds of things.
I know that I did an activity when I first was introduced to this idea of computational thinking. We actually analyzed primary source documents, and they gave us a choice of using these different documents. And the two documents that we used, one was a statement from the Bureau of Land Management regarding the seizure of some Native American land. And the second document that we analyzed was looking at the response of that group and reacting to kind of what is happening, the actions of the BLN. And what we did is we analyzed the types of words. Our data was the words themselves, which to me just blew my mind, because as a humanities major, it's like I've never really looked at text this way. But we analyzed the types of words that were used, and then we graphed them and so on. And it was, for us, it was a mind-blowing experience. But I think, again, from social studies, there's just all kinds of things that can be done that way, and it's a different way of looking at it and interpreting what we look at and kind of take at face value. So it's an interesting one. I know that the data collection is not necessarily one of the traditional indicators for computational thinking. Usually data is kind of implicit in the four categories or the four areas, and I really appreciate the fact that they've mentioned data in here, because that again can translate into almost any content area.
Yeah. Okay, so the next one is 5C. Students break problems into component parts, extract key information, and develop descriptive models to understand complex systems or facilitate problem solving. So when you work with, especially in elementary school, but as you work with that, is there anything that jumps out on you that you've seen or relationship you can make with that to across other content areas even?
I think the power in this one is taking initially a problem that could be overwhelming to students and facilitating them breaking it down into smaller bite-sized pieces.
Yes, excellent. Yeah.
A group I worked with read several articles on pollution problems around the world, three different pollution issues, and then picked one and developed their own solution to it, and then built a model of it. The idea of the Great Pacific garbage patch, huge problem that seems bigger than something we can tackle, but then they were able to break that down. They went through this step, broke that down into smaller pieces, and ultimately developed their own solution to clean it up.
So the reason that is computational thinking is because that's the way machines and artificial intelligence and so on basically processes. That's the way you design computers. That's the way you design and program software, is that you essentially get it down to binary choices, and it becomes smaller pieces so that it's manageable and it can go through the various processes that are defined. So this idea of breaking things, complex ideas down, I think is something, again, that is not just something that you do with computers. You can do it in social studies, you can do it in math, and again, as you get more complicated, as you move up, in high school and so on, the problems get more complicated, and I think students can kind of get like, oh my gosh, I'm not sure how to attack this. And so this is really about a basic strategy for kind of attacking a challenge or a problem.
Yeah, and I think, and I would totally agree with that. I liked Wayne's example of having these articles. So you have a problem that may be big. You might have a large set of data or in a stack of all sorts of articles, right? And being able to extract the key information out of there, then be concise enough to write something or create something based off of that. That is a basic writing skill. And so making that connection for teachers, I think, is key as well.
So the two algorithmic terms that are used can be associated with this is decomposition, which is that activity of breaking things down, and then abstraction, which is doing the data sorting and basically moving things into the right categories and such. So our last indicator. There we go. Jeez.
Indicator.
Jeez, I'm sorry, ISTE. I've been voted off the island. The last indicator is students understand how automation works and use algorithmic thinking to develop a sequence of steps to create and test automated solutions. So this seems like we're talking a little bit about robotics, about automation, maybe even about artificial intelligence.
Maybe some coding,
Yeah.
if you were going to be the one to program something.
Yeah. So what are some things that you've done with kids that are kind of connected to this standard?
Automated solutions. I come back to the robotics work that I've done with the hummingbird kits. And students have an idea of how they want their end project to work as someone interacts with it and triggers one of the sensors. In that sense, it becomes kind of an automated piece of equipment. And so, when the room gets dark, the LEDs turn on. Or when someone walks by, it actuates some servos and there's some action happening. But they have to think through that, if this happens, then my robot's going to react in a particular way. So it comes to mind for me.
Yeah, and the hummingbird, that kit, some people may not be familiar with that, is really kind of an open-ended, it's a set of like LEDs and servos and sensors that are not, it doesn't look like a robot. It's basically just a box of pieces, and then students use cardboard and other materials to essentially insert those various bits in there and basically make their own robot using some of the tools that are in the hummingbird. So there's really a construction and a design and a creation, not just simply pushing some buttons on a pre-made robot.
Yeah, and even beyond that, not following the instructions in the manual so that everybody builds the same robot in the end. But it's very open-ended, as you said. A box of components that they can do whatever they dream of, imagine.
And that word test kind of jumps out to me too.
Mine too, yes. That's what I was thinking too, because they could have wrote that standard and they could have said develop a sequence of steps to create automated solutions. But they put that word test in there, and I think that's really interesting, and I think that's very wise of them. And the fact that this may not work every time, and that idea of iteration and going back and having to problem shoot and troubleshoot your own work.
Yeah, in the activity that we do with the Legos, just this weekend when we did it with the ELL teachers, we did a show of hands, and it's a very simple activity where you have to create, take 5 pieces of Lego and create a replicable algorithm. You write it down and then pass it on to somebody else, and then they try to replicate it. And I asked the group how many people succeeded, how many people were able to get their algorithm to be repeated by the person that they gave it to. About a third of the people did that. And then I said, how many of you beautifully failed? And 2/3 of the people rose up their hands. And I think, one of the things I kind of pulled out is that idea of iteration and replication and failure, problem solving is something that we don't do in classrooms very often. And I think that's one of the things with computational thinking. It gives us an opportunity to kind of change the conversation about instruction. So, Zach, any last thoughts?
Not on this one. I think this one's almost, for me, it gets a little more technical, than the other standards. But I think it's just because, personally speaking, I'm a little bit further removed from that world. The jargon and language that starts to come in with this. But through both of your guys' work and some of the work you've done in the district, for me, it's been able to break down some of those barriers and connect it to things that are already happening in my work and already happening in the classrooms.
So Wayne, why should teachers care about computational thinking?
I think it is critical that we are raising up problem solvers. And kids who can think for themselves and see problems, identify them, break them apart, and create solutions for those. In talking to the industries out there, one thing that they consistently repeat to me is we're looking to hire people who can kind of quote, think for themselves, or be creative with problem solving.
Yeah.
And it seems that there's a little bit of starvation out there around that. So
Sure.
I think computational thinking is a great avenue for teachers to explore.
Yeah, despite those big words like
Yes.
algorithm
Yep.
and decomposition. Yeah, I think it's a great equity. I think it's a great equity opportunity too. When you think about, coding and computer science has historically been kind of the domain of some students and
Yeah.
some groups of students that have access to that. I think the opportunity with computational thinking, if we can move it across the different content areas, is that everybody has the opportunity to learn how to be problem solvers and critical thinkers, and potentially then become the coders and programmers
Yes.
that will design these things for the future. All right, with that, we've come to an end. It's been great talking about computational thinking with Wayne, and this is Mark Ray,
And this is Zach Desjarlais.
and thanks for tuning in to EdTech Remix. See you next time.